devices it is getting connected through wires or wireless, then it is called circuit. Okay, but here it produces an output having the square wave, triangle wave, or sawtooth waveform called non-sinusoidal or relaxation oscillator. Okay, then the name you just keep it in your mind. Non-sinusoidal oscillator is also called relaxation oscillator. This is the question. This is the question they will be asking. Okay, this non-sinusoidal oscillator is also called relaxation oscillator, but sinusoidal oscillator is also called, no, first one is called harmonic oscillation. Okay, harmonic oscillation. So okay, anyway, so then it is providing output frequency ranging from 0 Hz to 20 megahertz. So the main question will be that non-sinusoidal oscillator, maybe that is from our frequency range or whatever, or what is the name. Okay, that is another name which is given for the non-sinusoidal oscillator. It is the relaxation oscillator. Okay, so anyway, nature of sinusoidal oscillation, nature of sinusoidal oscillator. Even okay, we can simply say that is depends on our frequency. Oscillation, it is called frequency signal. Oscillation, it is called frequency signal. But you are having one circuitry. Okay, that electronic circuit, which is the each and every element and devices, it is having some parameters. Okay, the parameters may not be constant. It is highly dependent on our temperature. It is highly dependent on our temperature. That parameter. That's the reason they are fixing that some tolerance. Okay, some tolerance level. So due to that parameter change, if that electrical oscillation whose amplitude goes on decreasing with time are called damping oscillations. Okay, it is not perfect oscillation. So because of the parameter of the internal devices or elements which we have used for creating our oscillator circuitry. In our oscillator circuitry, one circuit you are having, that in that oscillator circuit, okay, if you are using more number of electronic devices, then elements, then circuits, then something we are using. Okay, so while using that electronic devices and elements, it is having some parameters, common parameters. Suppose if you are having one resistor, means then 10 kilo ohm resistor means it is having only exactly, it cannot be exactly 10 kilo ohm resistor. Then according to the temperature difference, they are giving some tolerance level. Okay, if it is in gold, then it's 5% or something, whatever. Okay, then some tolerance level they are giving 1 kilo ohm, that may be that 1005, then 1000, that is 10. In between that it is giving some values. Okay, according to the temperature variations. Okay, so that every device and every electronics elements, it is having some what is that parameter change according to our temperature. So due to that oscillation will not be that amplitude of the oscillations which is produced by the oscillator circuitry, that amplitude will get changed, either keep on decreasing with time or called damped oscillation. At one point it will become a zero, like capacitor. You just imagine that capacitor that in DC. Okay, so once it is getting charged, every time it is small, like lightly it is depleting, it is getting discharged lightly, then it's every time interval it is going to down the voltage amplitude. Okay, so likewise here also the oscillation which is created, it is also going to decrease every time interval. That oscillation is called damped oscillations. Okay, damped oscillation. That it is not that much suitable. It is not very good in our oscillator circuitry. Now, this is the thing we required, undamped oscillation. Then electrical oscillation, here you can see that the amplitude is not going to decrease. So the thing is, the parameter may not be may not be fixed. Okay, parameter of the elements may not be fixed, but according to that tolerance level, if you are designing, then it is getting achieved. But 100% it may not be possible for getting the undamped oscillations exactly. Okay, so anyway, electrical oscillations whose amplitude remains constant, which is called undamped oscillations. But this is the only thing we require in our oscillator circuitry. Okay, now the oscillator circuitry, how it is performing. Okay, then here normal LC, this is tuned circuit. In our remote you are having in our remote and all. So there you are using tank circuit. This is called tank circuit. You can call it as tank circuit or oscillator circuit. Okay, so you can take it as here. What is happening? it is not getting, switch is not getting connected, assumed that capacitor is completely fully charged. You just keep it in your mind. Capacitor is assumed, okay, by external sources or whatever. After completely fully charged, it is connected in our device. Okay. Now, according to that parallel plates, positive charge is connected. Positive charge, more number of positive charges are accumulated on the that positive plate, and negative plate is getting that negative charges. So that is the common thing. This is the common thing. But even though it is common thing, we just know, we just aware of that, we just want to know that, okay. Then when it is getting connected with inductor, okay, when the capacitor is getting connected with inductor, what is happening? Okay, that is called tank circuit. That is the main motto, that is the main circuitry we are having in our entire oscillator circuitry. Okay, it is not giving any supply, but which is device that the capacitor is acting as a, that is source of the energy when it is getting connected. See, when SC is closed, figure 1, what is happening, the from the capacitor, when immediately that from the capacitor it is getting discharged, build up a magnetic field around the coil. Okay, magnetic field around the coil. So that is negative to positive, that circulation is happening because of that flow, that electron flow. Current is different. The current is from positive to negative. The electron flow from negative to positive. So here we are, here the negative, that is flowing, that is electron is flowing from one side to another side, which is creating, okay, that is coupled, which is creating, okay, the magnetic field around the coil due to that capacitor energy. From that capacitive energy, discharged capacitive energy. Okay. Now the second one is so completely it is discharged. Completely. Once if it is completely discharged, due to that back EMF, you are saying no, back EMF, counter EMF, back EMF. Normally we are saying that. So this kind of back EMF, it is getting generated. It is getting generated in our DAC motors. Okay, for that reason only they are giving some capacitor in between. Okay, that is bypass capacitor they are using. Okay, you just keep, if you are belongs to electrical, then that you will become to know that. Okay, that is back EMF. Okay, so when that is completely discharged, then from that reverse polarity, from that inductor, that energy is restored in our capacitor, that is happening in our reverse polarity. Polarity is changing. The reverse, because of back EMF or counter EMF, according to Lenz's law. Okay, the capacitor is charged with reverse polarity because of the back EMF, not exactly. Okay, back EMF, so which is opposite to our previous charge. Okay, now the capacitor is getting charged. All the positive charges is accumulated in our negative plate, and positive plate is getting accumulated by negative. So likewise, it is going on again after fully, that is charged of the capacitor. Again, the process is getting repeated. Then from the capacitor, that is in a reverse. So you just imagine that when it is from positive to negative, which means that is capacitor to inductor, if it is moving, positive cycle. You can take it as, because of it is taking some time interval, no, for discharging entire signal, when entire charge, for discharging entire charge, it is taking some time interval, no, that every time interval it is giving some small voltage. So anyway, so from that, so when the capacitor to, when the accumulated charges, when the discharges through that inductor, that time positive off cycle. Then when it is reverse polarity, because from that inductor, because of the back EMF, it is getting discharged from the inductor to and capacitor, then it is negative off cycle. Then another time, then positive, negative, then reverse polarity. Then likewise, it is creating like an oscillation. It is creating one oscillation, one time variant signal. That is the only thing, because it is having some time delay, no, for discharging the capacitor. So time variant signal we are receiving. So this is the only thing, because of back EMF, we are getting that reverse polarity. The reverse polarity means what? Because of we are receiving that negative off cycle. Why we are receiving the negative off cycle means because of reverse, because of counter EMF. Okay, so anyway, okay, then continuous charging and discharging is alternating motion, of course. This, so but interchange of energy between L and C produce that we know. In ideal circuit, there is no losses. Okay, we know that in ideal circuit, there is no losses. This oscillation continues indefinitely. We know that. But in practical cases, it is the tank circuit also. It is having some losses according to capacitor reactance and according to inductive reactance, according to some that is physical parameter of the capacitor and inductor. It is having some losses. That is, in practical cases, surely there are some loss. Due to these losses, damped oscillations is produced because which is not suitable for us, which is not efficient for us. Which one we require? That undamped oscillation is very good for our oscillator circuitry, but it is not possible. But natural resonant frequency of the tank circuit will be Fr is equal to 1 by 2 pi root LC. That is belongs to that is L and C, capacitor and inductor. Okay. Here practical oscillator circuit. This is the thing. Okay. Now after the oscillation is getting created, what we need to know that? First we need to go for amplification. Even the because why means that signal which is created by the capacitor and inductor, that oscillation which is created by the capacitor and inductor, the tank circuit, which is very small amplitude wise, very smaller. Okay, that amplitude is very smaller. So we need to amplify that. So when you are going for amplification, there is for monitoring for monitoring, there is one feedback network. This is the common practical oscillator circuitry. Amplifier is used for that is amplifying the weak signal which is created, which is generated. Weak signal means weak oscillation which is generated by tank circuit, that is going to amplify and that is going to strengthen by the amplifier circuitry. So that feedback, as usual, we know that is going to control. Okay. So anyway, this is the practical thing. Now, because till now we haven't come to our discussion, because that our discussion is there is what a sinusoidal oscillator. Our discussion is entirely sinusoidal oscillator. So here two different kind of oscillators we are having: sinusoidal oscillators and non-sinusoidal oscillators. Okay, but here in our discussion we are having that sinusoidal oscillator. Even though before that we just want to know that these all the things. Okay, now we just want to know the factors affecting the oscillator frequency. Okay, so which is creating one oscillation. That oscillation is completely related to our frequency. Frequency is completely related to our time period. So time period between the for the complete cycle. Okay, so it is that is time period. If it is an undamped oscillation, the time period is constant. That you know. Okay, but amplitude also constant. Okay, if it is an amplitude also will be constant if it is an undamped oscillation. But damped oscillation it will not be there. But in according to our practical application, practical circuitry, it cannot produce exactly that is what undamped oscillation by the oscillator circuitry. But even though, so we are close to that. Okay, we are reducing 70 or 75%. We just want to receive that. But factors affecting why it is getting affected. Why such undamped oscillation to that oscillator circuitry producing from damped oscillation, undamped oscillation to oscillation, the damped oscillation. Some reason is I simply said that that is because of that parameter of the parameter of the internal elements and devices that I told you that. Now from that some important factors they are using. One is operating point of the active devices, that is BJT. You know that what is active point? That active point, that is operating point or Q point, that should be placed according to our previous discussion. That should be placed exactly middle of the active region. Okay. So in our output characteristics curve. Okay. So that we have discussed on today. So if you are clever, if you have studied well, then you will come to know that. So that operating point of the active device, okay, may be changed. Maybe that is near to saturation point. Maybe that is near to cutoff point. That is moving into near to cutoff point or near to saturation point. So that's the reason. That's the reason may affect that oscillator frequency. Okay. Then second one is temperature dependency of the circuit. I said this is the only thing. This is the culprit is doing all those work. Okay, all those problems in our electronic circuitry. Temperature can't be constant because now in our real time 20 maybe in our side in our area 27 degrees centigrade, 26 degrees centigrade. Likewise, it is getting fluctuated. Now when you are going to the highly hotted area, okay, Okay, there you can find that that may be increasing, that is 29 to 30, like that it may increasing. So there also it should get support, that our device which is we have generated, which we have created by the manufacturer, there also it should get supported. Okay, then when you are going into the that is very very cold areas, that means like Kerala, there and all, that is like Jammu and Kashmir, there and all. Okay, so that may be temperature maybe like 13 or 15, like that, 15 to 15 degrees centigrade. There also our devices should give support. Okay, for that they are simply given that tolerance, that's all. So till that it can support, but even though it will support, it will get support, but it is having some drawback. Okay, the parameter is itself, we cannot use it exactly. Okay, we cannot find every time, we cannot test how much that is, because there is, when once you connected into a circuitry, according to our what is that external temperature, that parameter may get changed. Who will know that? Okay, because of the parameter, that oscillation, that oscillator frequency will get affected. The changes in DC supply. Okay, this thing we won't normally do that. Okay, so the oscillator circuit VCC, we are pointing out VCC. Okay, in our amplifier mostly we are using VCC. No, likewise here also we are using that. If you are using that what transistor, BJT transistor, there surely we are using VCC. Okay, VCC is our DC supply. Suppose if you are designing your oscillator circuitry for 12 volt DC supply, then that if you are changing that DC supply for 11 volt or 15 volt, likewise it is changing, means then it is creating a problem. It is creating that oscillator frequency is getting affected. Changes in output load. Okay, an output load for creating. So this thing you may see that in our microprocessor, microcontroller and all. Okay, according to that output load also it is getting affected. Then presence of what is that inter element capacitance. This thing mostly you are using FET, field effect transistors. Okay, somewhere. So somewhere for oscillator circuit you may design with what is that FET MOSFET transistor. Then inter element capacitance. Okay, that means what is that capacitor in capacitance created in between the gate and source. Then one more thing, one more is there, when you are going to connect all the devices, all the what is that oscillator circuitry devices and elements in our particular within a small area of the what PCB board, that every that is devices and elements, it is very close to each other. Because of that, it is creating some what capacity effect in between of every element or devices. So that is also playing a role for affecting that what oscillator frequency. Okay, so the types of sinusoidal oscillator, this is the thing we required, we want to know that. Okay, types of sinusoidal oscillator, this much of types we are having. First one is tuned circuit oscillator. Okay, in our tuned circuit oscillator, under the category we are having a tuned collector, Armstrong oscillator. Okay, this is also one of the questions they may ask. Okay, Armstrong oscillator. Okay, that which is also called. Okay, simply they may ask clap oscillator, Hartley oscillator, tuned base oscillator. Likewise, they can ask, but your answer should be tuned collector oscillator. So that's the reason I have segregated like this. The tuned collector or Armstrong oscillator. Okay, the tuned base oscillator, Hartley oscillator, Colpitts oscillator, clap oscillator. These are all coming under the category of tuned circuit oscillator. Okay, the tuned circuit oscillator mostly related to LC circuit, tank circuit. Okay, LC circuit. Okay, so that very first we have seen now that common. That is oscillation procedure for creating that oscillation. We have used some LC, that is inductor and capacitor, charged capacitor, which is connected very parallelly. So that is always belongs to tuned circuit oscillators. Okay, so from that, another one is RC oscillators under the category of sinusoidal oscillator. The second category is RC oscillators. Under RC oscillators, we are having two subdivisions: phase shift oscillators, Wien bridge oscillators. Okay. Then another one is crystal oscillators. Likewise, it is having the 3 or 4 subdivisions. Mainly, I have taken the three. These three only. Mainly, we are focusing everywhere. So that's the reason because there is lot of oscillators nowadays. It is getting generated. Okay, the created by designer, by researcher. Okay, because mostly we are using. Okay, in our electronic circuitry, these are the oscillators. Okay, now first one is tuned oscillator. What is tuned oscillator? It is also called LC oscillator. Just now I told no, just keep it in your mind. So LC oscillator, because mostly in our oscillator circuitry in depth, if they are asking me, then what is the another name of particular oscillator. Okay, if it is tuned oscillator, it is also called LC oscillator, resonant circuit oscillator, tank circuit oscillators. See, so this much of names are there. See, for one, and along with okay, so it can produce 1 megahertz to 500 megahertz. Hence, this is known as RF oscillator, because the RF signal can be, it is having some, that is from megahertz to, then it's 500 megahertz. If it is getting produced, if it is producing, it is coming under the category of RF oscillator. Then BJT and JFET is used as an amplifier with the tuned circuit oscillations. Okay, either we can use that BJT and FET MOSFET also we can use. Who will ask? Okay, depending upon the way of feedback is used in the circuit, the LC oscillator is divided into different types. Okay, first one is tuned collector or Armstrong oscillator. These all the things. These all the subdivisions in our under the tuned oscillator, which is categorized, okay, based on the way of feedback which is connected, which is used in the circuit. How we are using, how we are connecting, how we are feedback, how we are using the feedback, okay, how we are fixing the feedback in our circuitry, which is giving that differences, which is giving that subdivisions. Okay, tuned collector oscillator, okay, like tuned base oscillator, Hartley oscillator, Colpitts oscillator, Clap oscillators. Okay, now tuned collector oscillator, Armstrong oscillator, the common structure is there. Here you can see that one transistor they have used. Then in our collector region, in our, because one tank circuit there is must, because according to our tuned collector, it means tuned, sorry, what is that, tuned oscillators, according to the discussion of tan, that is tuned oscillators, which is the base, that is LC circuit is the base. Okay, LC circuit is the base. So from our LC circuit, if it is interconnected according to our charge, then the charging and discharging process, the oscillation is getting created. The oscillation is getting created from our LC tank circuit. So here L1 and L2 is playing a role of tank circuit. Then is L1 is coupled with, okay, L2. That is like a transformer. That is like a transformer. You can take it as that is like a transformer. Okay. Now that is L2 is given to the input of base, the input to the base, then voltage divider biasing is happening. R1 and R2 is playing a voltage divider biasing. Then C is bypass capacitor. Of course, we said already. Here, one more thing we require, one more important thing we just want to know, that when you are discussing about the tuned, that is whatever the oscillator, internally 360 degree, what is that, phase shift we require. Okay, at last, because from our signal, we should receive, because if you are using that amplifier, that means one transistor from the input, okay, that is phase shift, okay, that is given 180. That is transistor itself, it is giving that 180-degree phase shift, because it is not sufficient, because it is going to zero. It should start from zero. It should start from that waveform. It should start from zero or 360. 0 or 360. So that's the reason. So totally 360-degree, okay, phase shift which it requires. Likewise, you can say that then very fast, okay, very fast 60-degree, what is that, oscillation, okay, 60-degree phase shift. It is that from the zero, it will move to what? It will move to negative to, according to our quadrant, it will move to negative and negative, fourth quadrant. That arrow will move to, so I can show you that. Okay, that later I'll show you that. Okay, so anyway, so here, so totally 360-degree, that is phase shift which required. Okay, you just keep it in mind always, that here the transistor, because of the common emitter transistor, here it is, we are using common emitter transistor. Because of the common emitter transistor, we are receiving 180-degree phase shift. We know that according to amplifier characteristics, amplifier properties, we know that, okay, that output of the capacitor is common emitter amplifier, common emitter, what is that, amplifier, likewise on transistor, common emitter transistor, okay, their output side, we are receiving 180-degree phase shift. Another 180-degree phase shift is received by L1 and L2, that is like a, what is the transformer, that is like transformer. See here, so everything has been given. Okay, see here, the tuned circuit or tank circuit. Okay, the secondary transformer provides AC feedback, that is the feedback voltage, okay, that appears across the base emitter junctions. This thing I have explained. 180-degree phase shift is provided by transistor. Another 180-degree phase shift is provided by what is that transformer totally 360 degree. 360 degree is equal to 0 degree. Okay, you know that when supply given, okay, the operation of that tank circuit is, okay, tank circuit is when supply given. Supply means what? They are pointing out VCC. VCC is the supply. When supply given, IC gets start increasing. IC starts increasing and charging the capacitor C1, because initially it was not getting charged. No, initially it was not getting charged. So immediately the capacitor is getting charged. Okay, immediately the capacitor is getting charged. When C1 is fully charged, it discharges through the L1. So again, the process is repeating like the previous one. Like previously I said, no, that is charging and discharging, charging and discharging. Likewise, the process is happening. Output of the inductor, we are receiving what? That is looped into a, what is it, amplifier. Amplifier is doing the amplifying purpose, amplifying operation. So that you get the base of the transistor here, base of the transistor which is receiving oscillation signal. That means oscillator signal. The oscillation is created by C1 and L1. You got it? So then output is also output we can see in our amplifier. That is our collector of the what? Common emitter. What is it? Transistor. Common emitter transistor. So the amplified form is we are receiving in our output side. This is the tuned collector oscillator. Okay. So it is now oscillation is produced. Now the oscillation is produced, which induce some voltage in secondary winding. So of course, whatever I said. So at last, so the produced oscillation, okay, mostly such kind of oscillator, mostly we are using for radio receivers. That oscillation frequency of oscillation. Okay, oscillation is getting created. We don't know, we are not aware of that. What is the frequency it is having? That oscillation, there is oscillation, that means AC signal, which is created by the tank circuit, which is looped, which is feedback to the input signal, the input, that is base, which is given into the input, that is base. Then what is the frequency of the oscillation? That we want to know that. Okay, so that is given by F output, the means oscillation. Oscillation frequency, if oscillation frequency is equal to 1 by 2 pi root L1 C1. You know that what is L1 and C1. From that L1 C1 only the oscillation is getting created. So it is related to L1 and C1. See here. So then second, then tuned base, then there also okay. Okay. Then second kind of oscillator is tuned base oscillator. Tuned base oscillator. So here RE and or CE or stabilizing circuit. See, stabilizing circuit. It is giving that what? Stabilizing circuit. Here it is getting connected. So VCC is getting connected. So VCC is giving, it is connected with voltage divided by as R1 and R2 and along with L1. Okay, L1. Then L2. There is two. Okay, so like what is that? Step down transformer. That is, what is that? Center tap transformer. You just keep it in mind. Center tap transformer. Okay, in between we are having a terminal like that. Okay, so L1 and L2 is coupled with L. Okay, so that is, so then here also from the VCC the signal is getting okay. So in our input side, then it is creating, that is linked with L. Because of the L, the charge capacity is getting charged. See here, when supply is given, IC starts rising, which creates a magnetic field to the coil L1. See here, so it is creating, because of that, it is creating, because of the DC supply which is received from that VCC. Because of that VCC, that L1 is getting energized. That means it is creating magnetic field. See here, so which induces the voltage in tuned circuit coil. That L1 is giving, that is coupled with, what is that? Coupled with L. So L, that means inductor L is getting energized, which is getting magnetized from that. So again, that process is getting repeated from charging and capacitor of the capacitor and L1. So now further increase in IC that's achieved and the cycle continues. In the meanwhile, the capacitor is fully charged. When IC reaches saturation, there is no feedback voltage in L. So okay. So likewise, the continuous process is happening, that is charging and discharging. Okay. As the capacitor is fully charged, it starts discharging through L. This decrease the emitter base by, okay. So now this increase the emitter base bias. As a result, IC increases. The cycle repeats. At last, what we are receiving, similar manner, whatever we have. So but the thing is that we are not aware of that. We are not supposed to use that much. That is, we are not disturbing collector of the what transistor. Okay, so that's the only thing. We are applying that base, that tank circuit into base. There we have applied the tank circuit in collector. That's the reason collector tuned oscillator. Here base is getting connected with tank circuit. So that's the reason. That is what is that? Tuned base oscillator. Okay, it is also giving exactly same f o is equal to 1 by 2 pi root L1 C1. Here one drawback is there. Drawback is reduces Q point poor stability. We will see that. Okay, by maintaining the stability of oscillation is maintaining. Okay, that amplitude and the frequency of the signal, oscillated signal, oscillation signal, which should be maintained as constant. Okay, sustained manner. Okay, that's the thing. Now Hartley oscillator here. Hello. Okay. So anyway, Hartley oscillators. So here you can see that. Okay, that inductor and capacitor. The two inductors we are using L1 and L2. Then inductor L1 is connected with L2 parallel manner because of the in between what one is what is the ground potential is there. Okay. So anyway, not that is along with capacitor. Okay. Here capacitor is what is the variable capacitor. With the help of variable capacitor, we can create different what is different frequency of oscillation. You got it? So previously it was not like that because fixed according to our capacitor and inductor, that is fixed. Whatever we have used in our circuitry, that is fixed. See, you can see that. The capacitor and inductor value is fixed. So only one specified that frequency of oscillation is getting created. But here that variable capacitor is getting used because of the variable capacitor. Then at last in output side we are receiving what exactly? Sorry, that is different kind of that is frequency of oscillations. Okay. Here as usual, the CB is used for what is that? The coupling capacitor. Okay, and it's blocking. We can call it as not blocking capacitor. Input side we are using means there is blocking capacitor because it is blocks or blocking capacitor is used for blocking DC content. Okay, then coupling capacitor is used in output side because capacitor, same capacitor only we are using. Likewise, if it is connected in input side, then that is called blocking capacitor. If it is connected in output side, that is called coupling capacitor because of it is going to couple with another circuitry. Okay, another circuitry like this. So here also, here the radio frequency choke offers very high impedance to high frequency currents, which means in charts of DC and opens in AC. Here we have used no choke RFC. RFC is there. Okay, radio frequency choke. Okay, so which means the shorts in DC and which is short circuit in DC, which is open circuit. That means open circuit in what? AC. Okay. So anyway, so hence it provides DC load for collector and the AC current out. Okay. Both. Okay. That is not a matter. But the thing is, where we are receiving that what is that oscillation? That oscillation is created by both coils L1 and L2 are inductively coupled and together form an auto transformer. Okay, because of the inductively coupled. So why we are saying that transformer means because there is a primary winding and a secondary winding. If primary winding and secondary winding is coupled, then it is called transformer. Here inductively coupled. Okay, there is no use of it. So automatic transformer. So then when collector supply is given, okay, that auto transformer. Why they are specifying the name auto transformer means the transformer itself, it is giving 180-degree phase shift. Our thing is 360. The solution is 360-degree phase shift. If it is every oscillator circuitry which should provide 360-degree what is that phase shift. Okay, so that's the thing. So when collector is given, transient current is produced. Of course, the collector current is produced in the oscillator circuitry. Sorry, the transient current is produced in our oscillator circuitry, tank circuitry. Oscillator current in tank circuit produces AC voltages across L1. AC voltages across L1. Okay. So anyway, so here, so at last, the one structure wise only is changing. Okay. So one more thing, here we are using two capacitors. Okay. Of course, the same procedure, whatever we have discussed in the previous, very first. Okay. From charging and discharging. So when the inductor is getting charged, capacity is getting depleted because of from the capacitor is getting depleted or discharging. Okay, from the discharging energy of the capacitor, the inductor is getting energized from the energy from the reverse polarity, from the reverse manner. Okay, according to our back EMF or counter EMF. So from the reverse according to the reverse polarity Lenz's law, it is giving that reverse supply. Then the capacity is getting charged. Then it's getting that is inductor is getting de-energized. Okay, the frequency here also the same procedure only, but the thing is how much we are receiving, how much we are receiving in our Hartley oscillator. Then frequency of oscillations F is equal to 1 by 2 pi LT. See, because here we are using, that is LT is cumulative coupled inductance, because the inductance is coupled. No, cumulative coupling inductance is LT is equal to L1 plus L2 plus 2M. M means mutual inductance. M means mutual inductance. So if anybody is asking, okay, anybody is asking about if some problem, okay, some problem with the help of what Hartley oscillator, simply they have given the value L1 and L2, L1 and L2. So from that we can M also mutual inductance also they are giving nowadays. Okay, for you don't have that much time for practicing for doing that work in our what is that gate examination. So for that mostly they will be giving some values. Okay, according to M you need to find that L1 and L2. Okay, so then from that you can go for the frequency of Hartley also. This thing we must know that F is equal to 1 by 2 pi root LT and CL. LT is cumulative coupled inductance. Advantages here, it is having some advantages Hartley oscillator, because this Hartley oscillator is the mostly used. Okay, okay, anyway. So advantage, it is having some advantages. Instead of using large transformer, a single coil can be used, because you see here some advantages. Here previously we have used two transformer in our tuned circuit. Okay, capacity, sorry, collector tuned circuit. We have used in our collector oscillation, collector tank circuit oscillation to couple with base. We have used one transformer. Okay, that is separate transformer. So here it is not necessary to have used that any of the transformer, because inductor in place of inductor itself is framing as a one of the auto transformer. Okay, it is getting reduced. So one entire device, one big device is getting reduced in our complex circuitry. So the frequency can be varied, because the thing is, as ultimate, in our ultimate, our thing is, I have already told you that invention means it should reduce the space. Okay, so you may use that, because previously once upon a time it was one computer means it was like one complete room. Okay, when it is getting created, one electronic numeric what is that computer, it was that much big of size house size. Okay, now you see here one computer is this much only, one computer, one some mobile phone is this much only. Okay, so the space is getting reduced. While reducing that space, then some capacitive effect is present in that. Okay, because of that only some heat is getting generated, because of that very narrow space in between the devices or in between the elements. It is creating some capacitive effect. It is creating some heat. So likewise, some parameter is getting changed. Okay, even though stray capacitance, somebody they are saying the stray capacitance and all. Okay, but even though that space, if the space is getting reduced, because we are always focusing on, we are not supposed to focus on lifetime nowadays. You just keep it in your mind. When somebody is, you may finding out that research. Okay, when you are reading your research paper and all, every wire they are specifying that what reducing the energy, reducing the space, reducing the devices. Likewise only they are focusing. The thing is, it is not like that. Our main focus should be lifetime. You see their old computer and old what is that televisions and all, it may use till the 20 years or 40 years, like that they may use till now. It is working some of the houses and all. Okay, but our new generation, that is television and radios and what computer and all, it may not be, maybe 5 years or 60 years only it is applicable. So they are not giving any warranty or guarantee for that, for working. Because even though the electronics is good, it is, they are not completely focused on what? Lifetime. Okay, lifetime. Okay. So, so that here also likewise, the transformer which we have used previously, that is going to reduce. Okay. Instead of the transformer, separate transformer, one single, the two coils is enough. Okay. Then auto, that is acting as a auto transformer. So which is giving 180-degree phase shift. Okay. Then another 180-degree phase shift is created by transistor. You got it? Another 180 degrees. So totally 360. You can find that every oscillator should have that 360-degree phase shift. That is very important. You at least you write in your examinations also. Okay, that is very important. Okay. So anyway, so that frequency of oscillations is like that. Advantages. Okay. Then this advantages. One more advantage is the frequency can be varied using variable capacitor. That already I told that, because previously it was, that provision is not like, not there. So in our previous oscillator and all, the provision is not there. Okay, the provision has been given here only. Frequency can be varied using variable capacitor. So we can generate, because that is like a potentiometer, like a potentiometer. Okay, potentiometer is normally resistance, variable resistance. Okay, so like a capacitance also, capacitor also can be varied. Okay, with the help of, this is also like one of the what voltage divider biasing for creating by your own board, for creating. So like parallel capacitor, series capacitor. Then if you are connecting the two capacitor seriously, then what is the total capacitance? Then 1 by C is equal to, sorry, C is equal to C1 into C2 divided by C1 plus C2. So that is the thing. If you are connecting parallelly means C1 plus C2. So just reverse. See here. So that the thing they are using here, variable capacitance. So because of the variable capacitance, we can find at last we are receiving exactly what is that frequency, variable frequencies. Okay, previously it was not like that. So one disadvantage is there, it can't be low frequency oscillator. It is applicable for it high frequency oscillator. Okay, so Colpitt's oscillator. Okay, there we have used only one change, nothing else. Okay, there is only one change. Okay, one, as usual we are having one transistor. Okay, RE and CE. RE and CE is used for stabilizing the circuit, stabilizing effect. Okay, then transistor is used for amplification. Then RF, as usual, RF choke is there. Then R1, R2 is used for what? Voltage divider biasing. Capacitor CB is used for what? Blocking capacitor, that is used for blocking the DC signal. Okay, DC voltage. Okay, then DC of the signal. Then coupling capacitor also is doing the same work, but even though it is doing the same work, but it is going to couple with another stage, with the next stage. Okay, here you can find that instead of the two inductors, here they are using two variable capacitors, one inductor. Inductor means, inductor, if it wants to get energized, the output which we have taken from, what is it, inductor. So that capacitor and the inductor, that two loop of the capacitor and inductor is creating oscillation with the help of VCC plus VCC. So VCC is on top. From the VCC, we are receiving, that is energy, that is supply, that means voltage is getting stored in our C1 and C2. Then from that C1 and C2, then that loop is getting, that is inductor L is getting energized. So charging and discharging after inductor, and after completely depleted, and from the inductor it is getting charged back by C1 and C2. So at last that loop is getting continuous. Then positive and negative pulses are getting created, which is called oscillation. That oscillation is we are taking in our output side, which is coupled like a transformer. This is also acting as a transformer. You see here, two inductors are getting coupled, so that is one of the transformer. So the output is oscillation. Okay, so now see here, only one change is there. Only one change is there. When the collector supplies, okay, as usual, the oscillator current is thanks to the producer. AC voltage is, because why I haven't given that means only the concept is charging and discharging. At last, frequency of the Colpitt's oscillator F is equal to 1 by 2 pi root L CT. Why I am giving that CT means, okay, total capacitance. The two capacitors are connected. Okay, parallel manner. So CT is equal to C1 C2 divided by C1 plus C2. Why? If both are connected in parallel, sorry, series manner. So not series, parallel, series manner. So if both capacitors are connected series, C1 and C2 That 1 by C1 plus 1 by C is equal to 1 by C1 plus 1 by C2. So C1 into C2 divided by C1 plus C2. So that's the thing we have used to, instead of capacitor, the inductor, here in our Colpix oscillator, we are using capacitor. Okay. So anyway, advantage it is one when we are using instead of inductor, capacitor, when we are using, some advantages we are facing. It generates sinusoidal signal of very high frequencies. Frequency stability is high. Okay. Frequency can be varied using the two, that is C1 and C2. Amplitude of the output remains constant over fixed frequency. Applications used as temperature sensor with some circuitry, used as local oscillator receiver, likewise. Clap oscillator. The third one is clap oscillator. This is the structure they are having. So the remaining things are same. Only the tank circuit is getting changed. Here we are using three capacitor instead of two capacitor. Here we are using three capacitor coupled with, then is connected along with inductor. So that is creating the C1 and C2, C3 and L is creating what? Oscillation or oscillation. Okay. So the output is taken from, that is L. Of course, the same L we are using another one inductor that is taking as an output. Okay, that is like a transformer. L is considered as a transformer. You just imagine that from the previous discussion. Okay, that is we taken output is taken like what? One more inductor is connected in our coupling manner, like a coupling manner. Here also we should connect one coupling what is that? Inductor, which is acting as a transformer. Now the transformer, it is creating 180-degree phase shift, and transistor is creating another 180-degree phase shift. So totally it is giving that 360-degree phase shift. Now because that is the ultimate aim we should have. That is because as usual we can receive from our previous discussion, as usual we can receive the charging and discharging process, because from that VC supply, from the VC supply, the capacitor is getting charged, inductor is discharging. The process continues repeatedly happening. Okay. Now from that, okay, the amplification also is done. From that amplification, because it is connected to base, no, it is connected to base, no. So from that, it is acting as a feedback loop. It is acting as a feedback loop. Feedback is positive feedback. Feedback is positive feedback. Always you should have in your mind. Oscillator means positive feedback. Amplifier means negative feedback. You just keep it in your mind. So at last it is creating a feedback loop. So inductor itself, it is connected with one of the transformer, like it is behaving as a transformer when it is connecting as output. When output is getting connected, output inductor also is getting connected. It is acting as a what? Inductor, that is transformer. Okay. So now from the transformer, okay, we are receiving 180-degree phase shift. Transistor we are using another 180-degree phase shift. Totally at last 360-degree phase shift. So clap oscillator, it is giving that it improves frequency stability and eliminates the effect. So operations wise, clap oscillator is in the same way as that of Colpix oscillator. Frequency of the clap oscillator is getting varied. Okay, because there we have used only two capacitors. Here we are using three capacitors. So all three are seriously connected. So at last CT is equal to C1 into C2 into C3 divided by C1 plus C2 C3. Okay, C2 plus 3 C3. So this is called what? Till now we have studied about tuned circuit, because tuned circuit is belongs to what? L and C. That the circuit is having, the trans circuit is having L and C. Only capacitor and inductor. So it is having one huge drawback. Okay, some huge drawback. Okay, frequency instability. That is very big problem when you are using LC tuned circuit. LC tuned circuits. LC tuned circuits. What are the categories we are having? That is collector tuned circuit. Then base tuned circuit. Then what is that? Another one is Colpix oscillator. Then clap oscillator. Then what is that? One more. So likewise, so these all the things only belongs to what? L and C combination. So it is having some problem. Waveform is poor, cannot be used for low frequencies. Inductors are bulky and expensive. Mostly inductors, because till now we are not having that. Nowadays they are producing. Inductive IC. Okay, IC, or that is inductor is they are fixing, they are creating as an IC. Till now it is in research. It is in research. Now some of the ICs are already getting created. But in our Tyagarajar college and all, they are till now some research is going on. One of my friend who is doing that same research. Okay, so inductor on chip, inductor on chip. The topic name is inductor on chip. That is very big area. Till now there is not that much solution, because one inductor means we are just rotating. That is like a spring. Spring is there, no? Spring is there, no? So for creating, so that is too bulky for creating that much for absorbing that much for what is that? Energy, okay, inductive energy, okay. So inductors are bulky and expensive, okay. Now the second, so to overcome these drawbacks, we are going for another one, RC oscillators. RC means instead of LC we are using RC. LC means inductor and capacitor. Instead of inductor and capacitor as a tank circuit, here we are using RC oscillator. Then previously I said that when it is when you are connecting inductor and capacitor, simply we can take it as, okay, simply that is energy, that is charging and discharging process. It can easily deliver. It can easily creating oscillation. But with the help of RC oscillator, the output, this is the basic structure RC. The C is connected in, because here also the charging and capacitor from our V1. V1 may be V1 is DC or AC, whatever. Okay. The thing is that while after getting the charging, okay, till it won't allow. Okay. So the charging and discharging process of the capacitor is playing a role here. Okay. It is also having some phase angle, So output voltage V1 across the resistor R, okay, leads the input voltage. So you know what is leads and lagging? Leads and lagging. So leads means the pace leads and pace lagging. Okay. So if in pace also is there, another one name is there. In pace is in pace. Current is in pace. Somewhere you may hear the word current is in pace. Current is out of pace of the voltage. Likewise, something you may hear about the word. Okay. The thing is, in pace means once the signal is started from, the signal is started from zero. The first signal is started from, the current voltage signal is started from zero. Zero is the origin. Now, the second signal, current signal, also is started from same zero. Then it is called in pace. It is called in pace. Both the waveforms, both the current and voltage waveforms are in pace with each other. Okay. If it is having that leading, okay, then first we starting from zero. We starting from the current, the voltage waveform is starting from voltage sine wave. You just keep it in your mind. Sine wave voltage is starting from zero. Voltage waveform is starting from zero. Then current waveform is starting from minus 90. You got it? You got it? Minus 90, which means 90-degree leading. You got it? 90-degree leading. Okay, leading. So then if 90-degree, if after 90-degree that second waveform is getting started, means it is lagging. Okay, so that is the, because that, it is creating pace angle, which is creating, yes, pi degree, which is creating pace angle, which is creating pace angle. So the thing is, where it is getting started, the starting of the waveform may be changed. That pace angle, that which is called pace angle, because angle, which is creating one angle. Okay, so pace of the signal. Okay, the output voltage V1 across the resistor R1 leads to here output voltage of the voltage V1 across the resistor R1 leads the input voltage V1 by some pace angle pi 0. Adjusting R0 to 0 would be the impracticable. Okay, actually by adjusting, actually thing is if R is 0, then that is creating exactly, that is creating pace angle good. Okay, that is exactly, that is 90-degree pace shift, it is giving 90-degree pace shift, it is giving if it is 0. Now, because actually our ultimate aim is, if it is an oscillator, our ultimate aim is what? 360-degree phase shift. You just keep it in your mind. Always the 360-degree phase shift it requires. Okay, 360-degree means 0. If it is started means again that second one also, that second waveform also, output waveform, input output relations, nothing else. Input output relations. Okay, so that from that amplifier, from the feedback, if you are receiving 180-degree phase shift, Then when you are receiving in our output side, after crossing that amplification, the output you should in phase of the uh, generated oscillator circuitry. Why I'm saying is from the oscillation, first initially it is moving into what tank circuit or transformer. It is moving into transformer to couple. Okay, then the transformer it is creating 180-degree phase shift. That means then zero is shifted into 180-degree. The starting point of the zero waveform is moving to 180-degree. 180-degree. Okay. Then due to that another 180-degree phase shift of what? Phase shift of transistor. Again, it is moving into 360-degree. 360-degree means is equal to zero. So which is called, so that is, but that, so that's the thing we have done previous thing. So here when R is equal to zero, that phase difference, that means phase angle is 90-degree, but it cannot be in practical. It is not possible to reduce zero voltage, zero resistance. That is not possible, no, in practice even. So because it would lead to no voltage across R. So in practice, R is varied to such value that makes V1 to lead by 60-degree. Okay, 60-degree. So there's capacitor and resistor RC RC network is creating 60-degree by adjusting the R value. We are fixing it 60-degree. Values only, no, we are going to change. So anyway, it is adjustable. So by adjusting, we are doing that by varying the resistance. By varying the resistance of the resistor, we are fixing with leading V1 lead to that is 60-degree. 60-degree. So to totally 180-degree phase shift the feedback. So here C1 R1, C2 R2, C3 R3 is should give 180-degree phase shift. Should give 180-degree phase shift. That another transistor is giving another 180-degree phase shift. So feedback is given taken as C1 R1, C2 R2, C3 R3, which is forming as RC phase shift. RC phase shift. So which is giving that phase shift. Okay. So anyway, 180-degree phase shift it is delivering. So totally at last we are receiving an output side. So 360-degree phase shift. Another 180-degree is given by transistor. Okay. So when collector supply is given, oscillates resonant frequency F0. The output A0 amplified is fed back to the RC feedback network. This network produces phase shift 180 degree, and the energy appears at it. So at last we are receiving that frequency of oscillation is equal to 1 by 2 pi RC, then root of 2n. N is equal to number of RC feedback stages. Here, how many number of feedback stages are there? 1, 2, 3. C1 R1 is one stage, C2 R2 is another stage, C3 R3 is another stage. So totally 3 stages are there. If anybody is asking to find frequency of oscillation for the RC phase shift oscillator, this formula we should apply. So O is equal to 1 by 2 pi RC root of 2n. So where n number of RC feedback stages. So another one is, so this is also classified into two types, no, RC oscillators also is classified into two types. One is RC phase shift, another one is Wien bridge oscillator. So this is the Wien bridge oscillator. This is the common structure. Here you can notice that one bridge is there. Like commonly there is rectifier bridge is there, no, bridge rectifier. How we are connecting? This is the manner, no, we are connecting in bridge rectifier. Okay, rectifier and all. I think you haven't seen. Okay, I think tomorrow the next class they are having. The rectifier is getting connected. There is rectifier, there is bridge. It is like a bridge. So it is having such structure only. So I hope everybody you know about them, because that was very easy. Okay. So anyway, here one resistor which is connected R3, R1 and C1 is connected another loop, another hand. Then C2 and L2 is connected parallelly as another hand. Then LP is connected. LP means tungsten lamp. Okay, it is connected is another end. So totally 4 hands are there which is connected. Okay, so now that is the output of that bridge rectifier is connected to input of the T1, then output of the T1 is connected to input of the T2. Here 2 amplifiers. You just imagine that Transistor is doing the operation of amplification. Because why I'm saying means here also it is there focusing on 180-degree phase shift. There is 360-degree phase shift. Okay. The thing is here we are not supposed to use that any of the transformer to supply any of the phase shift. What is that RC network? We are not supposed to use here. So where we are receiving, that is 180-degree phase shift means 360-degree phase shift means one T1 is producing 180-degree phase shift, then another T2 is producing another 180-degree phase shift, totally 360-degree phase shift when it is receiving in our output side. When it is receiving in our output side. You got it? So here the transistor 1 is used as an amplifier, then transistor T2 is used as an invert operations, because of that is positive to negative. Common emitter amplifier normally is giving that positive. Is if you are giving the supply input side to positive to negative, then output side you will be receiving negative to positive. So just 180-degree phase shift signal we are receiving in our output side. So that similar manner when it is given into the input of the T2, then the similar manner it is going to happen. It is going to happen in our output side. There from the negative to positive, again it is shifted into positive to negative. See here, it is two times it is getting amplified. Even though it is getting amplified, we are our ultimate focus on what? The 360-degree phase shift. See here. So this is mostly used because of its important feature. The circuit is free from the circuit fluctuation and ambient temperature. Here R3 and the LP are used to stabilize the amplitude. It is two-stage amplifier with RC bridge. Here it is served. See here, this is the important point we should require. The transistor T1 serves as an oscillator and then amplifier. While other transistor T2 serves as an inverter, which means the inverter operation provides a phase shift of 180-degree. See the common procedure. You see here that RC, it is feedback network. This is the simple diagram, which is equivalent circuit diagram. You can take it as equivalent diagram, because actually it is not equivalent circuit, equivalent diagram. You just take it as an equivalent diagram. Okay, this is the equivalent diagram of the Wien bridge oscillator. Okay. See the same network I have given the R and C, that is series and parallel connections, See that's the arm. That's the arm we are using now. That is R1 and C1, C2 and R2. So both are series and parallel now. So that same connections I have used here. An amplifier first stage, amplifier second stage. The second stage you see here. See the signal here. Signal positive to negative before amplifier one. Before amplifier one, the signal, the base of the signal is getting, base of the amplifier is received from that oscillation, from the oscillation of RC network, okay, by charging and discharging. The option is charging and discharging. Okay, so it is supplied by what? Supply voltage. It is supplied by supplied voltage. See here, supply voltage where it is. Okay, it is given. Okay, so anyway, so the positive and negative. So that positive and negative supply, positive and negative off cycle is changed as negative and positive output of the output of the amplifier one. Then again, after if it is receiving, again it is applied to the input of the amplifier 2. Then when it is getting amplified in our output side as an in our amplifier 2, there you are receiving just positive, just like that, equivalent to our input signal. That is phase is equivalent. So at last 360 degree. So 180-degree phase shift we are receiving the output of the amplifier. You see here, here you can see that 180-degree phase shift. Okay. Now, so that second one. Okay. So when the collector supply is given, bridge circuit produces bridge circuit. Bridge circuit means what? That we have given now, that bridge circuit is producing oscillation. The two transistor produces a total phase shift. Okay, this is the so negative feedback of the circuit ensures constant output, which it is achieved by temperature. Okay, tungsten, it resistance. Okay, if the amplitude of the output increases, more current is produced and more negative feedback achieved. Due to this, output would return to original. Whereas if the output decreases, reverse action would take place. Okay, here also we can take this formula. Okay, the frequency of oscillation FO, we can take it as FO, mistakenly at left. Okay, FO is equal to 1 by 2 pi root R1 C1 R2 C2, because R1 C1, so which is connected as series and parallel combinations. So the root is when if you are using R1 is equal to R2. Okay, the both values are values of the R1 and R2, values of the R1 and R2. Okay, then you can take it as R1 C1 in serial connection, series connection. See here R1 and C1 and R2 and C2. So both R1 and R2 are same, and C1 and C2 are same means the equation will become 1 by 2 pi RC, not root RC. You don't confuse that when you are discussing about that Wien bridge oscillator. When you are discussing about that Wien bridge oscillator, you just always you should have in your mind. So that is frequency of oscillation, okay, is equal to 2 by root of the whole root of R1 C1 R2 C2. If R1 is equal to R2 and C1 is equal to Z2, then surely that equation is becoming F is equal to 1 by 2 pi RC, not 2 RC, not 2 RC. You just keep it in your mind. Well, bridge oscillator, operational amplifier, the using. So those oscillators, everything is done by transistor circuitry. Transistor circuitry, okay, which is used for amplification. Transistor circuitry is used for amplification. Transistor circuitry we are mostly used for transistor is mostly used for what? Amplifier purposing. So weak, from the weak signal which is created, which is generated from our oscillator circuitry, that weak signal should be amplified, and it is giving in the it is giving as an amplified manner as an output. Okay, so for that only. So instead of transistor, we can go for this operational amplifier also. Okay, amplifier likewise. So the advantages, it provides good frequency stability, it provides constant output. Overall gain is high because of two transistors. Because of two transistors. Be silent. Okay. 1 minute, please. Hello? Are you there? Hello? I just want to check whether are you there or what. Hello? Hello? Anyone of you respond me? Yes, yes, yes. Okay, ma. Okay, okay. Okay, okay. 1 minute, 1 minute. 1 minute, ma. I have water, then let's discuss. Okay, time. We are having very less time. 1 o'clock we started. Okay. 1 minute, ma. Let me complete this one. Then we'll go for 5 minutes break. Okay. Drawbacks of tuned and phase shift oscillator. Okay. Till now we have completed tuned and phase shift oscillators. So what are the different types of tuned oscillators we are having? Collector tuned oscillator, then base tuned oscillator, Colpitts oscillator, Clap oscillator. Likewise, tuned oscillator we have seen. Then phase shift oscillators means then RC phase shift oscillator, then Wien bridge oscillator. So these all the oscillators we have seen. According to our tuned oscillators, what are the components mainly we are using? L and C, capacitor and inductor. According to our phase shift oscillators, which is we are using as a main component, then resistor and capacitor. So LC and here RC. That is the only difference. Now, so here also we have the both. It is having some drawbacks. That means the value of resistance and capacitance and inductance vary with temperature. The value of resistance, this I told, no, at the very first I told, no, that every component, every element, every device is completely related to our parameter of the temperature variance. Okay, temperature variations of the current environment. Okay, so these the values of the resistors and capacitance, when you are using the multiple number of devices, then multiple number of, so for creating the such circuits, such RC passive, main bridge, clap, Colpitts, and such kind of this much of oscillators. If you want to create oscillator circuitry, if you want to create there, you want to use multiple number of electronics elements as well as electrical elements you should use, because transistor is the electrical element, electrical device. Then the resistor and capacitor is electrical element. Then a transistor is the electronics device. So likewise, this much of devices and elements we are using, which is highly affected by temperature variations. Okay. So because of the temperature variations, we are not supposed to receive exact, okay, exact oscillations which we require, okay, which may affected completely. So hence the frequency get affected. So that is temperature is playing a role to avoid that, to avoid that. So instead of we are using this much of electronic components and electronics elements and electronic devices, okay, for circuit operation, for circuit connections, we are supposed to use only one crystal, okay, only one crystal, okay, you can see that, okay. So okay, so only one crystal because we are having, so this one only I will complete it, then let us go for what, so otherwise shall we go for what, break one, I think one hour completed, 1.5 hours completed, shall we go for a break, sir? I feel thirsty. You also maybe. Shall we go for break? You should say. I'm asking you, my dear students. For listening online classes, I'm telling that this may be boring. But thing is, you just record that when you are listening back, that time you'll come to know everything. Because we are having very less time now. Okay, this much because I need to complete a lot of portions. So that's the reason I'm doing this much fast. Okay, so I'm telling this much fast. So you please you collect that videos which they have or is recorded, then you will come to know everything. Okay, so silently, patiently you just listen somewhere else, like a story. Electronics very first I told, no, like the step by step procedure, step by step procedure. Okay, so that is like a story. You just keep it in your mind, just keep it in your mind. So I'm giving that free time. Okay, okay, now for you go for 5 minutes break, then you come back, please. Shall we go for, or otherwise shall I continue? Hello, I'm expecting your response. Whether I have to continue or shall we go for break? Hello. Yes. Okay. Anyway, it's up to you. You are being silent. I don't know who are all listening, who are all not listening. Okay. Anyway, but you please. Okay. You take a break, then come back within 5 minutes. Okay. Let's complete it. Yes. For for 5 minutes break. நம்ம 1 மணி நேரம் இருக்கா? போறாரு. ஒரு மணிக்கு ஆரம்பிக்குமா? ஒரு மணிக்கு ஆரம்பிக்குமா? நீங்க இங்க இல்ல. உடனே ஆரம்பிங்க.
Number 44. Satya number 50. Satya number 50. அதே ரீட் பண்ணுவாங்க. டெஃபினிஷன் ரீட் பண்ண. The electricity of demand in a market is great or small according to the amount demanded increases much or little for a given fall in the price and diminishes much or little for a given rise in price. Satya. Ma'am, Satya. அந்த டெஃபினிஷனோட அத லைவ் கிளியர்ல மியூட் பண்ணிக்கோ மியூட் பண்ணிக்கோ. ஓகே, உங்களுக்கு வந்து லைன் கிளியரா இல்லாததுனால I cannot ask Satya. So Ashwini number 6. Yeah, Ajita, you change your network. Okay, Ashwini. Ma'am. Is my voice clear for you? Audible alka? Clear. Yes, Ajit's network problem. Ajit, you please change your network. உனக்கு மட்டும் தான் ப்ராப்ளமா இருக்கு. மேக்ஸிமம் எல்லாருமே கரெக்ட்டா எல்லாருக்கும் லிசன் ஆகுது. உனக்கு தான் ப்ராப்ளம். சரியா? என்னமா? ரெண்டு நாளா ஜியோல நெட் இருக்குமா? ஓட போட்டு. சரி, அது பாக்கிடுங்க. ஏன்னா உனக்கு டெய்லி ரெண்டு நாள்ல ஜியோ நெட் போன் போட்டு. ஓகே. ஓகே, அஸ்வினி. இதுல என்ன புரியுதுமா அஸ்வினி? புரியுதா? இதெல்லாம் புரியலையா? அல்ஃபிரட் மார்ஷலோடைய டெஃபினிஷன் போட்டிருக்காங்க உங்க ஸ்கிரீன்ல. எலாஸ்டிசிட்டி ஆஃப் டிமாண்ட்னா என்ன அப்படின்னு அல்ஃபிரட் மார்ஷலோடைய டெஃபினிஷன் உங்க ஸ்கிரீன்ல தெரியுது. அஸ்வினிக்கு அது புரியுதா? ஓகே, தேவையின் நிகழ்ச்சி. வெரி குட். அப்படின்னா என்னதுமா? டவர்லாம் வெளியே போனா அட்ரன்ஸ் போடுங்க. ஓகே, அஸ்வினி தேவை நிகழ்ச்சி தமிழ்ல படிச்சது அழகா சொல்லிட்டேன். அப்படின்னா என்ன அர்த்தம்னு தெரியுமா? அது ஞாபகம் இல்லையா? Okay, mute your mic, Ashwini. Okay, students. So here elasticity of demand. Ashwini, mute your mic. So elasticity of demand அப்படிங்கிறது நம்ம பார்த்தோம் previous class. Elasticity, sorry, demand law, demand previous classல பார்த்தோம். நம்ம elasticity of demand பார்க்க போறோம். Elasticனா உங்களுக்கு நல்லாவே தெரியும். ரப்பர் வந்து எலாஸ்டிக் நெகிழ்ச்சித்தன்மை. அழகான வேர்ட் சொன்ன அஸ்வினி. ரியலி அவன் சொன்னனால அதிகம் பண்ணிருக்கேன். லாஸ்ட் இயர் அவர் சொன்னாங்க. ஸோ ஐ ஜஸ்ட் ரிமெம்பர் நவ் தட் எலாஸ்டிசிட்டி அப்படிங்கிற வார்த்தைக்கு நெகிழ்ச்சி அப்படிங்கிற மீனிங் தமிழ்ல. ஸோ எலாஸ்டிசிட்டி அப்படிங்கிற வேர்டு ஆக்சுவலா அதோடைய தமிழ் மீனிங் நெகிழ்ச்சின்னு இருந்தாலும் கூட வாட் வில் பி தி ஆக்சுவல் மீனிங், அதோடைய அர்த்தம் என்ன அப்படின்னு பார்த்தா நம்ம இழுத்து இழக்கிற மாதிரி வர ரப்பர் பேண்ட் எலாஸ்டிசிட்டி அதிகமானது அப்படின்னு நம்ம சொல்லுவோம். ஏன்? அதை நிறைய எக்ஸ்டென்ட்டுக்கு அதை இழுக்கலாம். ரப்பர் பேண்ட் அதுல எலாஸ்டிசிட்டி கிடையாது. மண்ணெல்லாம் எலாஸ்டிசிட்டி கிடையாது, இரும்புக்கு கிடையாது. பட் ரப்பர் பேண்ட் வில் ஹேவ் எலாஸ்டிசிட்டி அப்படின்னு எலாஸ்டிக் தன்மை உண்டு. அந்த எலாஸ்டிக்கும் என்ன சம்பந்தம் அப்படின்னு கேட்டீங்கன்னா, அந்த எலாஸ்டிசிட்டி ஆஃப் டிமாண்ட் அப்படிங்கிறது என்ன அப்படின்னா, the amount demanded increases much or little for a given fall in price. அதாவது நம்ம வந்து law of demand பார்த்தோம் previous classல. நம்ம வந்து கிராஃப் எல்லாம் பார்த்தோம். கிராஃப்ல வந்து மேங்கோஸ் வச்சு பார்த்தோம். பிரைஸ் வந்து ₹1 இருந்தா 10 மேங்கோ நம்ம வந்து டிமாண்ட் இருக்கு. பிரைஸ் 10 பார்த்தோம். அதுல ₹10 மேங்கோடைய பிரைஸ் ₹10னா டிமாண்ட் 10 மேங்கோ வேணும்னு மக்கள் வாங்குவாங்களாம். ₹10 இருக்கக்கூடிய பிரைஸ் மேங்கோடைய பிரைஸ் வந்து ₹20 மாறிச்சுன்னா பீப்புள் the demand of the இது வந்து என்ன ஆகும், பிரைஸ் வந்து அது வந்து குறைய ஆரம்பிச்சிடும். அப்ப என்ன பண்ணாங்க, அந்த டிமாண்ட் வந்து திருப்பி குறைய ஆரம்பிக்கும். So when the price is going on increasing, the demand decreases. So this is what we saw in law of demand. So இந்த elasticity of demand என்ன சொல்லுது அப்படின்னா, then price increase ஆகிற proportion அதனுடைய proportion ratio எந்த அளவுக்கு price கூடினால் எந்த அளவுக்கு demand increase ஆகும். நமக்கு demand தெரியும். whenever the price goes up demand increases, whenever the price decreases demand goes up. price கூடுனா demand குறையும், price குறைஞ்சா demand கூடும். அதனால demand ஓகே. ஆனா எந்த அளவுக்கு கூடும் எந்த அளவுக்கு குறையுங்கிற ஒரு ப்ரொபோஷன் இருக்கு பாத்தீங்களா, அந்த ப்ரொபோஷன் எலாஸ்டிசிட்டி அதை பத்தி சொல்றதுனாலதான் அதை எலாஸ்டிசிட்டி ஆஃப் டிமாண்ட் அப்படின்னு நம்ம சொல்றோம். ஃபார் எக்ஸாம்பிள் மேங்கோ வந்து 10 ரூபாய் இன்க்ரீஸ் ஆனா, மேங்கோ வந்து 10 ரூபாய் இன்க்ரீஸ் ஆனா 10 டிமாண்ட் ஃபார் மேங்கோ குறையும். இது சேம் லெவல்ல பேசு. 10 ரூபாய் மேங்கோ இன்க்ரீஸ் ஆனா 50% லெவல் குறையும். 50 மேங்கோ 50 குறையும் அப்படின்னா அது கூடுதல் இம்பாக்ட் இருக்கும். 10க்கு 10ன்றது அது ஒரு சேம் டைப் ஆஃப் இம்பாக்ட். ஓகே, ஒன்னு தனக்கு 1 ரூபாய் போடுறப்ப ஒரு ஒரு டிமாண்ட் குறையுது, 2 ரூபாய் போடுறப்ப 2 டிமாண்ட் குறையுது, 3 ரூபாய் போடுறப்ப 3 டிமாண்ட் குறையுது. ஸோ இந்த மாதிரி இருக்கிறது ஒரு நார்மலா போயிட்டு சொல்லலாம். 1 ரூபாய் போடுறப்ப 100 குறையுது, 2 ரூபாய் போடுறப்ப 200 குறையுது, 300 500 குறையுது. இந்த மாதிரி போடுறது வந்து ப்ரொபோர்ஷன் இன்க்ரிமெண்ட். ஸோ இதான் நம்ம எலாஸ்டிசிட்டி ஆஃப் டிமாண்ட் அப்படின்னு சொல்றோம். சரியா? ஸோ அதுதான் அவங்க சொல்லியிருக்காங்க, the fall in prices and diminishes much of the loss for a given raise price. பிரைஸ் கூடுறதுக்கு எந்த அளவு ப்ரொபோர்ஷன்ல டிமாண்ட் குறையுது அப்படிங்கறத சொல்லக்கூடியது. அதுதான் எலாஸ்டிசிட்டி ஆஃப் டிமாண்ட். சரியா? ஸோ பாருங்க, இது ஒரு டெஃபினிஷன் உங்களுக்கு ஒரு சிம்பிள் டெஃபினிஷன் தேவைனால அது சொல்லிக்கிறாங்க. உங்க ஸ்கிரீன்ல தெரியுது. Elasticity is the degree of change in demand as a result of change in price. Price மாறுவதன் போல, price மாறுவதை போல, how far the price changes, what will be the elasticity, the proportionate change, elasticity change. சரியா? அதான் proportionate, நெகிழ்ச்சித்தன்மை தமிழ்ல சொல்றது. So பிரைஸ் மாறுவதற்கு எந்த அளவில் நமக்கு டிமாண்ட் மாறுது அப்படின்னு சொல்றதுதான் எலாஸ்டிசிட்டி. சரியா? சொல்லோ ரொம்ப எலாஸ்டிசிட்டி இருக்கும், இல்லைன்னா குறைவான நிகழ்ச்சித்தன்மை இருக்கும், இல்லைன்னா நிறைய நிகழ்ச்சித்தன்மை இருக்கும்.
Hello, shall we continue? Hello, any one of you please respond me. I'm expecting some response from your side. Shall we continue? Okay, I hope everybody refreshed, you get refreshed. Okay, okay, so anyway, so where I left, crystal oscillator. So why the crystal oscillator is we are preferring crystal oscillator, reason is the value of the resistance and capacitance and inductance vary with temperature because of using multiple number of resistor and capacitor inductor. Okay, we are going for an opted device, okay, which is crystal oscillator, which means crystal, not crystal oscillator, crystal. We are preferring the device crystal. Okay, the crystal only we are going to use for creating oscillation, So if the crystal it wants to create oscillation, something we need to do that. Okay, actually the use of piezoelectric crystal, okay, mostly we are preferring, okay, okay, that oscillator for producing oscillation. Some of the specialized crystals we are using, okay, the use of piezoelectric crystals, okay, in parallel resonance circuit provide high frequency stability in oscillators, such oscillators called crystal oscillator. Oscillator, mostly the crystal oscillator we have used for microprocessor and microcontroller and digital devices. Okay, so we are not going for what is that LC circuit and RC circuit and all. Mostly we are preferring, this is the crystal oscillator we are using. So somewhere else, suppose if you are in your laboratory, when you are going to see that development board and development kit and all, there you could find something like some crystals. some crystals, okay, which is used mostly for electronics, which is, for generating timing signals, which means uh, oscillation. It is creating a frequency of oscillations. It is creating frequency of oscillations. That frequency of oscillations itself, we are assuming. So we are assigning, okay. So that timing signals, that is creating timing signals, okay. So anyway, so for that purpose only, we are mostly preferring the crystal oscillators. There we cannot use one more board. There we cannot use one more board for getting oscillations like RC phase shift, and then like what is that, like wave bridge. Likewise, we cannot add one more board. Only one crystal itself, it is generating, it is creating one oscillations, okay. So principles of, so there how the crystal is giving that what oscillations means, the principle of a crystal oscillator depends on piezoelectric effect. Piezoelectric effect. Then you can simply ask me that what is piezoelectric effect. So mostly the crystal oscillator depends on piezoelectric effect. So that effect is, okay, normally that crystal, when you are going to see the crystal is in the shape of hexagon shape, okay. Piezoelectric effect means when mechanical stress is applied across on the faces of crystal, the potential difference is developed across opposite face. Suppose if you are applying some press, some stress, that means by pressing mechanical press, that means by yourself, if you are pressing, the corresponding opposite side, some voltage, some developed, some potential difference is getting developed, okay. So that we can take it as, that we can connect to our external circuitry, okay, like footstep current electricity generation, like our footstep electricity generation, okay, AC supply, no, that and all coming under this category, okay. Conversely, when potential difference is applied, when you are applying voltage to one side, because there is hexagon shape, okay. So when you are applying that what is that supply voltage, that means potential difference on one phase, then opposite side, that vibration is getting created. Vibration means that is AC signal. Vibrations means that is called oscillation. That is itself, it is called as what, oscillation. So that's piezoelectric effect we are going to use for creating our crystal oscillators. Okay, you got it. So when mechanical stress is applied on one faces of the crystal, a potential difference is developed opposite side. Then reverse, when potential difference is applied, then here what is that? That oscillation is getting created. You got it? You got it? So likewise. So such a piezoelectric effect, okay. So examples of some crystalline materials we are having that based on piezoelectric effect, okay. Rochelle salt, okay, quartz, tourmaline, okay. So likewise, three different piezoelectric based crystalline material we are having. Mostly we are preferring among this quartz crystal, okay. Quartz is the most common used piezoelectric crystal because it is inexpensive and readily available in nature. Quartz, okay. When crystal is subjected to a proper alternating potential, okay, vibration mechanically. So according to our piezoelectric effect, when supply voltage is given, automatically the vibration is getting in our output side. So in the output side, vibration itself is called as oscillation, okay. So that oscillation, that frequency of the oscillation is the frequency of the alternative voltage which is created, which is generated at the output side, at the second end, is almost equivalent to, is related to our input voltage, okay. So when frequency of the alternate voltage is equal to natural frequency, one more thing, okay, when that vibration will be more, maximum vibration. So we know that maximum, okay, we know that vibration itself, it is creating that sine wave or whatever the waveform. That means signal is getting AC signal is getting generated, oscillation is getting generated. So then what is the maximum, whether it is amplified, whether it is frequency, then that is also, okay, when we are receiving means when that alternate voltage, okay, which we have applied, which is equivalent to natural frequency. But naturally, every crystal oscillator is having some frequency level. When it is equal, then it is becoming maximum. Then vibration is becoming maximum. So see here, this is the common connection. Here, that crystal inside one crystal is placed in between two plates. In between two plates. When we are applying that AC signal, when we are applying the AC signal on that plate, that crystal itself is getting vibrated. Okay, so that when you are taking output in our crystal, there you can find some oscillation, some what is that AC signal. So this is the common procedure we are having. So this is common crystal oscillator circuit. Okay, there in place of tank circuit, in place of RC circuit, you can find that in place of RC circuit, in place of tank circuit, we have used only one crystal which is connected to our base, in between base and collector. So capacitor is storage element. Okay, so likewise the previous, except the previous circuit, only one is different, that is instead of LC circuit, instead of RC circuit, they are using only one crystal as an oscillation, as an oscillator. So this is reducing the multiple number of elements, multiple number of devices. So it is creating, that is crystal itself, it is creating 180-degree phase shift also. So that 180-degree phase shift that is generated by crystal, and another 180-degree, that is also concerned. Okay, we must always focus on our 360-degree phase shift whenever you are discussing about the oscillators. Here, even though it is a crystal oscillator, it should also satisfy this condition. It should create the 360-degree phase shift. So with the help of transistor, it is creating 180-degree phase shift. Then crystal, it is creating 180-degree phase shift totally. And when you are receiving in our output side, at last there is 360-degree, that is phase shifted waveform. Okay, that crystal oscillator. Okay, here the frequency of the crystal oscillator is 1 by 2 pi root LC. Okay, that is LC. Inductance and capacitance is related to capacitance means what? It is pointing out. What it is pointing out? It is pointing out when you are placing in between two plates one crystal, that is acting as capacitor. You just imagine that. That is acting as capacitance, capacitive effect. Okay, then even though there is inductive effect also is applicable, so then F is equal to 1 by 2 pi root LC. It may be noted that the changes in supply voltage, transistor device parameters, etc., have no effect on the circuit operating frequency. This held, so this is the advantage we are having with the help of what crystal oscillators, by using the crystal oscillators. Mostly, it may be noted that the changes, if any changes in supply voltage, transistor device parameters have no effect, because see here, it is not applicable. It is not used based on our VCC. It is the vibration. So there is no effect on the circuit operating frequency, which is held stabilized in the stabilized by the crystal. That is advantages. They have higher order frequency stability. Quality factor of the crystal is very high. Quality factor. The disadvantage is there. The frequency of oscillations cannot be changed appreciably. Okay, this one more. This is the very big disadvantages in our previous discussion. So with the help of RC and LC, by the changing, by the use of variable capacitor, by the use of variable inductor, not variable capacitor, we can change. By the variable resistance, we can change that frequency of oscillations in our output side. Here it cannot. We want to remove that entire crystal oscillator. We should put some other crystal oscillator to change the frequency of oscillation. So if you want to create, that is 12 megahertz. Suppose if you are asking that 12 megahertz frequency, what is that crystal oscillator? So mostly we are using in our what is that microprocessor. 12 megahertz mostly we are using. Suppose if you are going to some other advanced microprocessor, there we should use what, some other oscillator frequency. That time we should remove that particular oscillator, what is that, crystal oscillator. Then we should use some other frequency level of frequency oscillator we should use instead of that 12 megahertz crystal oscillator. So that we cannot adjust. The thing is, we cannot adjust by varying the parameters of the capacitor and inductor. We cannot change, we cannot alter, we cannot increase or decrease that oscillation, frequency of oscillations in our by using our crystal oscillator. So that is the very big problem we are facing in our crystal oscillator. That is fixed frequency, it is getting delivered in our output side. So it can be used as low power circuits as usual. Then criteria of oscillations. I said no, the criteria of oscillations, Barkhausen criteria, I told no, very first, right? Barkhausen. So this is the common, what is that, oscillator circuitry, that is positive feedback. I told no, positive feedback, which is given to our, which is taken from feedback means interconnection between that something. You are having no, what, speedometer in your vehicle, in your vehicle speedometer having no, that is indicating the speed of the vehicle. Okay, that is vision, that is given as feedback, that is given as a visual feedback to our vision, so from that we can increase or decrease our accelerator. So with the help of that feedback circuit, we can assume, we can design, okay, that entire amplifier performance. So that's the reason mostly we are using feedback circuit. Okay, here the feedback circuit, which is taken from output side to input side. That feedback, if it is an oscillator, feedback circuit is, so what is the feedback circuit we are using in our LC tuned circuit? LC is the feedback circuit. Okay? Amplifier, sorry, transformer is the feedback circuit. LC, that is series capacitance, series inductance, both are acting as a feedback circuit. RC phase shift, the RC network is acting as a feedback circuit. Okay, then Vein bridge. So there also you are using that transistor is acting as a what is the feedback circuit. So likewise, every device, every oscillator circuit is having feedback circuits. Okay, so likewise, so feedback circuit itself, it is going to correct it. So now when you are going to discuss about that amplifier with gain we are normally notated as A. Feedback circuit gain is beta. We are giving that assumption. Okay, now Vs is equal to input signal. Okay, then V input of the amplifier, then V out is equal to output of the amplifier, then output of the amplifier as well as input of the feedback circuit. Then Vf is equal to feedback voltage will be, then partial output is received from our output voltage to input side, then beta is equal to V out. So Vf is equal to feedback voltage is equal to beta into V out. So gain into V out, because gain, we know that gain is equal to output divided by input. So according to our voltage gain, V output by V input is equal to beta. So that is the common thing. So V out by V input is equal to that is that beta. So Vf is equal to V input is equal to what? Then Vf here V input is equal to, in our feedback circuit, what is, which is the input voltage, V output is the input voltage, then Vf is the output voltage. So Vf is equal to beta V out. So that is given. Okay, so when you are giving, the voltage is added for positive feedback and subtracted for negative feedback. As usual, you know that when it is a positive feedback, voltage Vf and V input, okay, Vf and Vs is added, it is going as a V input because of positive, because the arrow mark indicated, no, the arrow mark. So according to the arrow mark, Vf plus Vs equal to V input. You see here, Vi is equal to Vs plus Vf because of the positive feedback. If it is a negative feedback, suppose if it is a negative feedback, the answer will be Vi is equal to Vs minus beta V out or Vf, Vs minus Vf, if it is a negative feedback. But according to oscillator property, positive feedback, the positive feedback is addition of Vs plus Vf is equal to Vi. So that's the thing. So is equal to, so at last Vs plus beta V out of gain, that is A is equal to V out. So V out by V input is equal to A divided by 1 minus A beta is equal to A feedback. Okay, so that's all. So AF is equal to overall gain. AF is equal to overall gain of the feedback, and so just a substitution, nothing else. So instead of VF, they have used beta V out. That is a substitution, nothing else. Okay. So if A beta is equal to 1, then gain becomes unity. A beta is equal to 1, then gain becomes unity. Okay. So then gain becomes unity, which means there is no output without any input. There is no output without any input. Okay. Then in these conditions, amplifier works as an amplifier, A beta is equal to 1. The condition, Barkhausen criteria, somewhere else they may ask in your examination, competitive examinations. Okay, so what is the criteria we are using? What is the criteria we are using as in our oscillation, in our oscillators? Okay, so as a Barkhausen criteria, that means A beta is equal to 1. That should be your answer should be A beta is equal to 1. The Barkhausen criteria is equal to they may ask Barkhausen criteria is, they may ask, okay, A beta is equal to 1, A beta less than equal to 1, A beta less than or equal to 1, A beta greater than or equal to 1. Likewise, they may ask, your answer should be A beta is equal to 1, Barkhausen criteria. Okay, this is the standard criteria which we are using in our oscillator circuitry. Okay, then frequency stability of an oscillator. This is the second important point. Frequency stability of an oscillator. It is defined as the ability of the oscillator to maintain the required frequency. We know that, okay? We know that the frequency, because always because why? When we are creating our oscillator, when we are using the oscillator circuitry, at last in our output side, we are receiving oscillation. That should be undamped oscillations, not damped oscillations. That should not be damped oscillations. So these time variant signal. So the frequency of the oscillation, frequency of the oscillation should maintain as constant. Okay, over a long time interval. So that is done by, that is called stability. Stability, like our stabilizer, we are having a constant voltage, even though it is fluctuated from 280 to what is that in our home, 280 to 150, 180, 280 to 180. So if you are using stabilizer in output side, you are using constantly 230 voltage. Mostly in our televisions, in our what is that, electronic components and all, it should use. Actually, it should use, because normally we are not using some of the electronic devices itself. It is contained. Okay. So anyway, but oscillations, that is what is that, sustaining. It should sustain a particular voltage itself, even though it is fluctuated, which is called stability. But the stability, that frequency maintaining as constant. Factors affecting the stability of an oscillator, as usual, I said that this thing we have discussed already: change in Q point, variation in temperature, variation in power supply, change in output load, and change in inter-element capacitance. This thing we have discussed. Okay. Anyway, now, so we are moving into another important topic. So this till now we have seen what oscillator circuitry, oscillations, how it is getting oscillated, what are the different types of oscillators. Then so there, what is the drawback we are facing in our LC? What is the drawback we are facing in our RC phase shift, RC oscillators? Then which is the advancement we are facing in our crystal oscillator? Everything we have seen according with the help of what, frequency of oscillations. Frequency of oscillations, also the formulas also we have seen. Now we are moving into that function generators. Okay, function generators. Functions mean different functions. Okay, it generates different functions, different voltage signals, functions. Okay, so in your laboratory you may have the function generators. Okay, there by pressing some buttons you can find that, you can in our oscilloscope you can find that it is changing as sine wave, it is changing as square wave, it is changing as triangle wave, it is changing as sawtooth wave. So likewise, that changing of different signal wave structure, different wave structure, because even though it is amplitude is common, the structure is changing. So such different functions, such different what is that, signals, okay, is called function generator. Generator of such different signals, such different voltage signals is called function generator. So each and every signal is called as function, because it is time variant signal now, that is called functions. Okay, so sine wave, sine function, pulse function, the triangle function, we can call it as then sine wave, pulse wave, and triangle waves. Likewise, we can call it as. So mostly in our digital and as well as analog discussion, mostly we are preferring sine wave and pulse wave. Okay, are most required to electronic circuitry. Sine waves are mostly, so according to our that is previous discussion, sine wave, that means AC signals. Okay, sine waves is mostly used in our analog circuit, like amplifier filters. Okay, so then pulse signals, like means pulse means what, square wave you are having, no, square wave and all. that and all coming under pulse signals. So pulse signals are useful in testing and time response, even that is what digital circuits. You can take it as we can use in our digital circuit. The general pulse signals, the high and low level time periods are different. Square wave is a special case when the period is are equal. When the period is equal. See, these are the different functions, different signals, voltage signals or functions we are using. The first one is sine wave. The second one is the shape of what is that, square wave. Then third one is pulse waveform. Because what then you can ask me, then what is the difference between that square wave and pulse waveform? You just see that negative what is that side, and only one pulse, that is width of the pulse is getting, it is not equal. It is not equal. Okay. So anyway, so likewise, it is going on. So that off time, when compare this off time, you can take it as negative side is off time. So on time, off time is same. Okay, on time, off time is same. If both are same, is then it is said to be square wave. Then pulse wave means off time is too large. So this is mostly we are receiving like in our capacitor effect. Okay, capacitor. So capacitor to getting charge, every capacitor to get charge, for getting charging, then it is taking microseconds. So when it is getting connected, immediately it is getting charged. For getting discharged, it is taking much time, much time. So that's the reason you are getting a slanting curve. You are getting slanting curve. So likewise, another one is then a triangle waveform is there. Okay, triangle waveform is there. Then sharp edges. Then another one is a sawtooth. The last waveform is sawtooth waveform. So this is the different kind of waveforms, which is called different functions, which is created by function generator. Okay. Now the common block diagram of function generator. This is the common block diagram of function generator. Here, what are the blocks we are having means frequency control network, frequency, then upper current source, lower current source, integrator, then voltage comparator, multi-vibrator, square wave amplifier, sine wave shaping circuit, sine wave amplifier. So likewise, so there at the output side, you can see that in output side, square wave output, okay, you are receiving from our square wave amplifier. Then sine wave amplifier, you are receiving sine wave output, but triangle wave output we are receiving from our integrator itself. Okay, integrator itself we are receiving. Okay, that means normally the frequency control network, which is controlling the frequency according to our current sources, different current sources. Okay, the frequency signals. Okay, that we can identify here. The two current sources are regulated by the frequency control voltage. Okay, if it is, if it wants, normally from our that is two current sources, immediately that is output of that current sources, which is connected with the integrator. It is connected with integrator. So integrator gets constant current alternatively from upper and lower current sources for equal amount of time repeatedly. This is the very important point. Then integrated gets constant current alternatively from upper and lower current sources, because there is two different what is that current sources. One is upper current source and another one is lower current source. Okay, so that is alternatively from upper and lower current sources for equal amount of time repeatedly. So the first time it is one, so the half of the time from the upper current source it is getting delivered. It is getting delivered. It is getting input to the what different integrator. Then after the time interval, after that half portion, then second half portion, which is giving that lower current source is giving the supply to what integrator. So that's the difference. Okay, that's the difference. So integrator will produce two types of outputs for the same time repeatedly. Two types of output. Current from upper source, the output voltage of an integrated increases linearly with respect to time. Okay, increases linearly with respect to time. With respect to time, every time interval. So due to that current from upper sources, output voltage of an integrator, okay, integrator is sharply increases linearly with respect to time. Then after the time interval, there is no delay, there is nothing, but immediately it is moving. It is current. The output voltage of an integrator decreases linearly with respect to time. That sharp edge also is there. So that is giving the signal of this triangle. That is giving the signal of the fourth image is there in a triangle. That triangle shot because of during that from that what is that upper current source. If it is getting delivered, the output is increasing. The output is increasing gradually with respect to time. With respect to time, linear motion. In linear motion, see here the linear curve you can find in our positive side. It is rising edge. Then after that particular interval, then immediately that is in our bottom. That means what lower current source is giving the supply. Is giving the supply. That time it is linearly decreasing. Okay, that linearly decreasing the output voltage with respect to time. So that we are receiving in our integrator itself that linear increment and linear decrement, it is creating the structure of what? Triangle waveform. It is creating a structure of triangle waveform. So we don't want to go for, we are not required to use another devices to create triangle waveform. That means integrator itself, it is creating according to that variation, according to that input supply supplied by different sources, different current sources. Okay, then at last in our output side we are receiving triangle wave output. Okay, so now so that our headache is to create square wave output and sine wave output. That is the question, because there we need to have some comparison. So that that square wave output and sine wave output, which is created from our triangular wave output only. So triangular wave output is given to the voltage comparator multivibrator. Okay, then what is that? Okay, then the same triangular waveform. So even though you don't worry about that frequencies and all, but the thing is how it is getting generated, like how we are converting that is from our triangle waveform, triangle wave from the integrator itself, we are receiving the triangle wave. Then from our triangle wave, how it is converted into square wave, that is given by in between two different modules we are having. One is voltage comparator, multivibrator. Then second one is square wave amplifier. Okay. Then from the voltage comparator output, which is given into the in upper current source input, that is also happening. Then if you want to convert into sine wave output, there sine wave shaping circuit, wave shaping circuit. So we are having in our discussion wave shaping circuit. So normally the clipper, clamper, differentiator, integrator, everything we are using, that and all coming under the category of wave shaping circuit. Okay. So that along with sine wave amplifier we are using. So at last in our output side we are using sine wave output. Sine wave output. So the comparison. See, so this is the, so till now we are receiving what is that triangle wave. That from the triangle wave, so we are getting supplied to our comparator, voltage comparator, to generate square wave. If the amplitude of the square wave that is produced at the output voltage comparator multivibrator is not sufficient, then it can be modified to the required value by using square wave amplifier. So the comparison is happening. So from our comparison, so delay is happening. So when you are comparing, so it is having the only two values. When you are comparing, it may have some threshold value. It is having some threshold value. Till threshold value, comparator means it is going to compare two values. Here from the integrator we are receiving only one value. From the integrator triangle wave it is receiving one value. Then from the what is that threshold value, it is fixed to the voltage comparator. So according to threshold value, the integrator value, it is going to compare with the integrator output, the triangle waveform output voltage. Then with the comparison, it is going to generate a square wave. So if it is lesser than that threshold value, that is fixed as 0. If it is greater than, so then average value you can take it as, then suppose that triangle wave, it is having amplitude 5 volt means 5 volt, the maximum amplitude. The maximum amplitude of that triangle wave, amplitude means height of this height of the waveform. So amplitude of the triangle wave is 5 volt means, then immediately, then 5 volt means, then if you want to find, if you want to go for, if you want to change it into a square wave, the threshold value will be 2.5 volt. So if it is the threshold, it is going to compare with integrator. Then if it is greater than 2.5 volt, the amplitude of the integrator is greater than 2.5 volt, it is considered as 1. It is considered as positive waveform, positive wave of the square. Then if it is lesser than 2.5 volt, then it is considered as zero. So either positive 5 volt or 0 volt, the only two options. Then it is becoming as square wave output. Okay, you got it. So now the second one is sine wave. 1 minute. Sine wave, basically the circuit consists of diode resistance network. If the amplitude of the sine wave produced as an output sine wave shaping circuit is insufficient, then the amplified is. So here what they are cleverly using, diode resistance network. Diode resistance network. Diode is forward bias when it is conducting, and reverse bias it is not conducting. So diode in forward side it is having zero resistance diode. Then in reverse side it is having infinite resistance diode, because like a switch, normal diode only, very first class we have discussed. So in our diode, so here it is applicable, that is diode resistance network is applied. So according to the diode resistance, according to that forward bias and reverse bias conditions, the shape of the that is triangle wave is changing, the sine wave is getting created with the help of what? With the help of what? Triangle, by using triangle waveform output. Now the wave shaping circuits, uh, that second module, no, that is wave shaping circuit, that is also one of the topic in our discussion. It may be either series RC and series RL circuit. Then series RC RL circuit, that and all becoming as integrator and differentiator. If you want to create one circuit for circuit like integrator and differentiator. Okay, integrator means what? Circuits are required to generate voltage, which are required to generate voltage. Okay, that means the group of voltages together, it is creating an integrated output voltage. So that is like a partial integration, no, we told, no. So differentiator circuit are used to generate sharp narrow pulses either from distorted pulses waveform or from rectangular waveforms. So the circuit used to perform these operations are called integrator and differentiation. So this thing, then one more wave shaping circuit is there that we have discussed previously, that is clipper and clamper. Clipper is also doing the function of what? What is that? Wave shaping function of wave shaping. So that is also considered as wave shaping circuit. Okay, so anyway, clipper and clamper, there also in clipper and clamper we are mostly using that capacitor and resistor along with our diode. So that is also acting as what? Wave shaping circuit. Okay, so anyway, 1 minute. Okay, so anyway, but this thing I need to show something for wave shaping circuit. 1 minute. 1 minute. I need to show something. See, wave shaping circuit. Okay, so listen here. See here. No need to go for that much. What is that thing? The topics, okay? Because we are not having that much sufficient time. The RC and the LC integrator and the differentiator circuit, that is acting as a wave shaping circuit. Storage, delay, and calculations of the speed of the diode clippers. Very first we have seen this thing, the diode clippers and diode comparator, clampers, everything also acting as an what? Wave shaping circuit. These three we have seen already. So that RL and the RC integrated and differentiation circuit only they haven't seen. That's that monostable multivibrator, bistable multivibrator, that we are going to discuss. Okay. See here. This is the thing. This is the thing we are using RC integrated circuit. There the input signal is applied to the resistance with the output taken across the capacitors. Then the V out equal to VC. So it is doing that. It is doing, okay. It is acting as a what is that wave shaping circuit, because of when we input is because of the storage element which is connected in our output side, but where only there is across the capacitor only we are taking the output also. So then according to the charging and discharging effect, okay, that shape of the input signal is getting changed. Okay, so that that capacitor is playing a role for conversion of the wave shaping. There is conversion where is wave from input side to output side. Okay. So as a capacitor frequency dependent element, that is the reason established across. Okay. Because why I'm saying means because that output we are taking across the capacitor. So that's the thing. So that is the time constants. The time is the because charging and discharging is playing a role. So the time is RC, the capacitor voltage last. See here. So this is the pulse. You can see here. So pulse shape is getting changed. No, the input pulse is input. So okay, this RL. Sorry, RC is here. Okay, sorry. RC is here. The pulse input pulse is having the 200 millisecond pulse. So when the charging time, the charging time it is when it is taking as an output side the capacitor across the capacitor. If you are taking as output, okay, there you could find that the charging time is very less and the charging time is very high, like a pulsating AC. But it is not completely because the shape is changing. But this is not used for us. This is not ultimately using for us. But the thing is, by the integrator, by the RC integrator, we can change the shape. We can change the shape of the. So RL integrator inductor is connected in series with source. So there, when you are doing, the signal is changing after crossing that resistance. The signal shape of the input pulse is changed in the like a flip. So the input signal is changed. The shape of the input signal is changing in different manner. So likewise, so that such kind of thing, we are having very less time. So likewise, there is change of shape. Changing the shape of the input signal is done by okay, is done by some of the specialized devices that mostly we are using the elements capacitor and inductor and along with diodes. With the application of diodes, if you want to use, okay, the help of diodes if you want to use, okay, so that is becoming as clipper and clipping circuit and clamping circuit. Okay, now the wave shaping circuit is used to perform any one of the following functions, that is surely must perform: to hold the waveform to a particular DC level. Okay, that is done by capacitor holding process means charging. We can call it as charging. The time interval means charging time, or that is related to charging time and discharging time. To generate one waveform to other, that means that wave shaping circuit means from the input signal is pulse signal, we are changing into some other manner like square wave or whatever, like what is that pulse and triangle wave. Like this, if it is changing means then pulse shaping circuit. Then clipper, it is some portion of the clipper means some portion of the waveform is getting clipped now. So that's the reason we are saying that to limit the voltage levels of the waveform of some presenting value and suppressing other values. This is the suppressing other values means here the category is coming under what? Clipper. Okay, to cut off the positive and negative portion of the input waveform, which is also likewise. Then that last portion, I don't want to make you bore. Okay, till now the something I have discussed, the only one portion I left, that is not that much left because I discussed many times multiple things about in our previous discussion itself. That is the clipper and clamper and comparator. Comparator means it is going to compare threshold comparator. No, I said no. So that's the reason the small portions I have that is taken very less time for that. Then the last portion is 555 timer. The 555 timer is one of the IC, okay, integrated circuit. Okay, it comes in a single or dual packages. Single packages also is there. Then from single, and you don't ask that what is single package, what is dual package. Okay, that and all coming under in our what is that VLSI design. Okay, even low power CMOS version, that name is ICM7555. The common part names are commonly we are having that 555 timer. If you are the purchase in your because timer is generating the timing signal. Okay, oscillation signal. That's all. Okay, you just keep it in your mind because normally when if you want to purchase in your market, then LM555, NE555, LM556, NE556, everything is having different configuration, different oscillations. Okay, the 555 timer consists of two voltage comparators, bistables, okay, bistable flip flop and discharge transistors. And so these what are the this is the block diagram of 555 timer. Okay, control one flip flop is available. Then threshold comparator, threshold comparator and trigger comparator, two comparators are there. Okay, to design. So that is control, threshold, and the trigger. Then is fifth pin. So that is what it means. That is 1, 2, 3, 4 something. They have given a pin number. So that is taken from pin diagram. Okay, pin diagram. So one is ground. One should be grounded. Two, we need to connect trigger. That three, we need to connect output. We need to take output. Then four, reset. Eighth pin VCC. So that that is like a integrated circuit. So from this, the internal connection will be like this. The threshold comparator is connected in between what 5 and 6. The pin number 5 and 6, control pin, threshold pin. Then threshold comparator, then trigger comparator is one input is connected to trigger input pin number 2. Then another one is taken from the what is that? Output of control input through one resistor R. Okay. Now that one transistor, okay, one NPN transistor, it is connected from Q bar. That means uh, uh, there is inverted output, which is connected to transistor base terminal. The output is taken. Output of the transistor, that is collector, is taken is connected with uh, pin number 7. Okay, pin number 7 means that is named as discharge. Okay, so that is voltage. Pin number 1 is connected to voltage divider. Okay, connected to voltage divider biasing, because R it is there no resistor 1, resistor 2, resistor 2, that is acting as a voltage divider bias. So that from the flip flop reset pin 4, then output is taken as 3. So this is the pin configuration, not pin configuration, internal diagram, internal block diagram of the 555 timer. Okay, so one flip flop it is getting used, then two comparators it is used. One comparator is threshold comparator, another one is trigger comparator, then another one is transistor is used for discharging. Okay, so anyway, the voltage divider has three equal 5 kilo ohm resistor. Okay, three equal. So see here, so R. So totally three resistors. So three resistors are 5 kilo ohm resistor. You know what is kilo ohm? So no, there is no time to explain. Anyway, it divides the input voltage VCC into three equal parts. The two comparators and are op amps that compare the voltages at their inputs and saturates depending upon which is greater. Okay, the threshold comparator saturates when the voltage at the threshold pin is greater than 2.3 VCC. VC. So VC, what is that? Whatever you are giving. Okay, so suppose somewhere else, 5 volt. I think 555 timer is should applied only 5 volt. Okay, the 5 volt is going to compare. Okay, so two third of 5 volt will be okay is greater than at the threshold pin. Okay, the trigger comparator, that time only it is getting. Okay, the trigger comparator saturates, that time only that is comparator is getting saturated. Then the trigger comparator saturates when that one third of, when the voltage trigger pulse is less than one third of BC. So that time it is getting saturated. That is comparator is getting saturated. Anyway, the flip flop is bistable flip flop, that we know that it can store the 2 bit of information. Either it can store high or 0. It generates 2 values. Okay. So when the threshold comparator saturates, the flip flop flip flop set output low signal at the pin number 3. When the trigger comparator saturates, okay, because when it will get saturate the trigger comparator one third of BCC, one third of VCC. So when the threshold comparator saturates two-third of VCC, two-third of BCC. Okay. So anyway, so that when the threshold comparator is saturated, that output of the flip flop will be the pin number 3 is low. 3 is low. Okay. When the trigger is getting comparator, when the trigger comparator is getting saturated, then output pin is high. Output pin is high. The transistor is being used as a switch. It connects pin number 7 discharge to ground when it is closed. When Q is low, this closes the transistor switch and attach the pin number to ground. When Q is low, Q means what? The output of the flip flop. The output of the flip flop is low. Then that time that Q bar is becoming 1. Then when Q bar is becoming 1, the transistor getting activated. That time the discharge process is happening. The discharge process happening. When that Q is 0, when Q is 1, that time Q bar is what is that 0. That time the transistor is getting off because of cutoff. Okay, so that time that no longer grounded, it is not getting grounded, so there is no discharging process. So this is the pin diagram. Then it is having operating modes. 1 minute, what is the timer? Okay, 1 minute, man. That is last. Almost we are near to complete. We are near to complete. Okay, you please. Operating modes of triple five timer IC: bistable mode or schema trigger. Okay, schema trigger. The triple five can operate as a flip flop if the discharge pin is not connected. This thing we can discuss. Monostable mode. Then three different modes we are using: bistable mode and bistable mode, monostable mode, astable mode. Monostable means only one pulse. Then bistable means two state. Okay. Then astable means free running mode. Okay. This is one of the questions. Astable means astable multi vibrator means whether it is one shot or bistable or what is that free running, like that they may ask. You just keep it in mind. Astable means free running mode. Okay. Example of the astable free running mode is pulse generator. Then monostable mode is pulse width modulator, and the bistable mode is bounce free latched switches. Okay. This is a pulse bistable mode. So there you can find that, okay, that discharge pin is not connected and no capacitor is used. You see here, discharge pin is not connected and there is no capacitor is used. So from this, okay, so on triple five timer which is connected on the likewise the two reset buttons, one is for a trigger button, another one is reset button. One two buttons, trigger button. When trigger button is pressed, some process happening. Okay, so the trigger and reset inputs pin 2 are held high. If both the inputs are high, pull-up resistor through pull-up resistors, while the threshold input is simply floating. Threshold input is simply floating. Thus configured, pulling the trigger to ground acts set and transition the output pin 3 to VCC. Pulling the reset, the pin 7 is left likewise. Okay. Monostable mode means here you see the trigger input. When trigger input is getting activated, the pulse is getting, and in our output side, monostable mode. Okay. So one shot operation. So here only one pulse is getting generated, RS. So here also likewise the two comparators it is going to play. Here when the pulse is triggered at pin 2, timer output will change to high for a while and change to low. This condition will continue until pulse is triggered again. So thing is, the pulse one shot means micro trigger. Okay, micro trigger. Okay, trigger means a small short that is trigger pulse. Trigger pulse. It is getting activated. Then immediately that action is taken by what is the flip flop. The flip flop is getting stored one till it maintains. Okay, the pulse generator circuit, which the period is calculated from RC network and connected to external of triple five timer. Threshold input monitors the voltage across C1 and likewise. Okay, so we are not supposed to make you bored. So anyway, astable mode is having free running. So on the output side, you can find that without what is that, any trigger pulse. You can here astable is very important thing is it doesn't require any what trigger pulse. Without any trigger pulse, it is the output is received as a square pulses. So like multi-vibrator, you can see astable multi-vibrator all modes as free running multi-vibrator. Astable do not need any. Okay, likewise. Okay, then see. This is the common thing, basic astable multi-vibrator. You see here T1 in our output side, we are receiving the free running signal. The T1, what is that? Time duration for one pulse, then off, that is during that off time, T2 duration it is taken. So now T1 time will be that 0.693, okay, into R1 plus R2 C1. Okay, then T2, the time duration of if you are using the stable multi-vibrator, then T2 will be that 0.693 R2 into C1. Frequency, that entire frequency, total frequency is equal to 1.44 divided by R1 plus 2 R2 C1. So the basic stable multi-vibrator mode, the entire at last the frequency is F is equal to 1 by 0.693 into R1 plus R plus 2 R2 C1. 1.44 divided by R1 plus 2 R2 into C1. So this is the common way we are using what is that triple five timer. Okay. Okay. So anyway, till now we have discussed about that oscillators, then what is that wave shaping circuits, then function generators, then what is that triple five timer, this and all we have discussed. There is mostly it is relate to our what is that generating our oscillation, generating our signals, okay, functions whether it is sine wave or square wave, whatever. But the thing is that entire circuit is generating pulses and signals, and which is called what is that function generations. Okay, at oscillators mostly we are using, so this much of oscillators we are having, we are classified at last. Preferred oscillator is crystal oscillator. Okay, so anyway, till now you listened patiently, so I so happy. Anyway, so hello, so I have completed my session. Any doubt means you can ask. Hello, hello, any doubt? Hello, sir. So you can, I have completed my session. You can carry on. Hello, sir. Hello, sir. Hello. Hello. Are you listening, or my audio problem you have? Anybody? Any one of you please respond me. Or is it audible, ma? Is it audible? Is it audible, my dear students? Yes, 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 yes. Okay, okay, ma, okay, okay. For listening and all, it may be complicated. It may be complicated. You again and again, I'm saying that once you get recorded means it will be clear. Okay, then you can pause. You can listen that what is the concepts are said, like that. You can take, because with this less time we can do this much only. There is no time. We need to be too fast. Okay, so that topic is too bulky. Okay, so anyway, I'm so happy. uh, uh, 1 minute. So I need to talk to 1 minute. Hello, sir. I have completed, sir, but nobody there. Shall I wind up myself? Yes, yes, yes. Okay, sir. Okay, sir. Bye. Because yes, sir. Because recording is going on, no. So shall I quit? Auto. Okay. Okay. Okay, sir. Okay. Okay. Bye. Bye. Bye.